So now we're ready to look at an example of using the first derivative test for extrema to find intervals of increase and decrease and relative extrema. So here's our function, 3x to the fourth plus 8x cubed plus 6x squared plus 7. So the first thing we want to look for is discontinuities. Well, this function is a polynomial, so there are no discontinuities. Now, we need to look for critical numbers. Well, remember, to find critical numbers, we need to look at the derivative. So we look at the derivative. F prime of x is 12x to the third plus 24x squared plus 12x. And so for critical numbers, we need to know, is this ever undefined, this first derivative, or is it ever equal to 0? Well, it is a polynomial, so it's going to be not only defined everywhere, it's going to be continuous everywhere. The first derivative is always defined for any value of x, so we won't be looking at cusps. So is it ever equal to 0? Well, let's set it equal to 0 and find out. Let's see if we can solve the resulting equation. Alright, so I think that factoring is probably the way to go here. I would look for a common factor, and there is a common factor of 12x. And let's see, that's going to leave x squared plus 2x plus 1. And then we can factor further into x plus 1 and x plus 1. Alright, so there are some solutions. This is going to give us x equals 0, and each of these other factors is going to give us x equals negative 1. So there are two critical numbers, 0 and negative 1. So I'm going to draw this out on a number line just to give us a guide. The two critical numbers are negative 1 and 0. Now, the only place that a function can change from increasing to decreasing or decreasing to increasing is at a discontinuity or a critical number. There are no discontinuities, and these 2 points, negative 1 and 0, are the only critical numbers. So those are the only 2 points where the function can change from increasing to decreasing, or either way, increasing to decreasing or decreasing to increasing. So if we figure out that it's increasing somewhere over here, then it's going to be increasing on that entire interval, or if we find out that it's decreasing somewhere in this interval, then it's going to be decreasing on that entire interval. So what we need to do is choose a test number. Now I've got a table set up that kind of organizes the data, and I think I'm going to use that. So we've got 3 intervals. We've got from negative infinity to negative 1, from negative 1 to 0, and then from 0 to infinity. Now I've put parentheses to remind us that we don't want to choose as our test numbers the endpoints. We need to choose numbers from the interiors of each of these intervals. And if you can, choose a number that's going to be easy to work with. Usually integers are better than some numbers, but not always. So I think I'm going to choose negative 2 for this interval. That's a representative test number for that interval. And then for this interval over here from 0 to infinity, I think I'll pick positive 1. And then we've got the interval from negative 1 to 0. Looks like we're not going to be able to choose an integer there. So any number inside that interval will work. If you want to pick 1 over 10, that's fine. 1 over 100, or negative 1 over 100, or negative 1 over 10, or negative 1 over the square root of 2. Have at it. I think I'm going to choose negative 1/2. Now, what am I going to do with these test numbers? Well, I'm going to put them into the derivative and see what signs I get. But I'm going to make use of the fact that we have already factored this derivative. Right? It's 12x times the square of the quantity x plus 1. So here's what I'm going to do. I'm going to put 12x, well, I'm going to separate 12x and the square of the quantity x plus 1, and I'm going to test the signs of each one of those at each of the test numbers. Let me show you. So we have 12x and the square of the quantity x plus 1. So what I'm going to do is I'm going to substitute negative 2 in for these values and check the sign of the result I get. So if I substitute a negative 2 for x, I get negative 24. The actual number isn't important, it's just whether it's positive or negative. Now if I substitute in the negative 2 for x plus 1, well, it's going to be positive because we're squaring. And in fact, that's going to be true for all the test numbers. The square of x plus 1 is always going to be positive. Alright, so what about the negative 1/2? Well, if I substitute that in here, it's going to be negative. And what about the 1? If I substitute that in there, well, that would be positive. Alright, so now what I need to do is figure out what that tells me, what this information tells me about the derivative. Well, remember that the derivative was equal to the 12x times the square of x plus 1. So what we've got on the third row and what we've got on the fourth row multiply together to get the derivative. So if one of the factors is negative and the other one is positive, then the derivative is going to be negative because a negative number times a positive number is negative. And then for the next row, for x equals negative 1/2, we've got a negative times a positive, that's negative. And then in the third column, a positive times a positive is positive. Alright, so far, so good. We have figured out that the derivative is negative on two different intervals and positive on the other interval. So are there any, well, okay, so what does this tell us about whether the function is increasing or decreasing? Well, if f prime is negative, that tells us that f is decreasing. And if the derivative is, again, for the next column, if the derivative is negative, the original function is decreasing. And for the last column, if the derivative is positive, then the original function is increasing. Alright, so do we have any intervals where the function is increasing and decreasing? Well, we do, don't we? So it's, remember that there was a theorem that we looked at that said that we can include the endpoints when we're looking at these intervals. So it's going to be decreasing on the interval from negative infinity to negative 1, including the endpoint. And then it's going to be decreasing on the interval from negative 1 to 0, including the endpoint. And then it's going to be increasing on the interval from 0 to positive infinity. Well, these first two intervals, the one from negative infinity to negative 1 and the one from negative 1 to 0, those intervals share a point in common. What we can do is just sort of combine that and say that the function is decreasing on the interval from negative infinity to 0, and then it's increasing on the interval from 0 to infinity. Now, if you don't like the idea of combining these into a single interval, I'm okay with you leaving them as two separate intervals. What about maxima and minima? Well, the function is decreasing to the left of 0, and it's increasing on the right side of 0. So that means we've got a relative minimum at x equals 0, that point right there. And to get the y-coordinate, we need to substitute the x-coordinate into the function. And that should give us 7. So, I know that this point notation and interval notation can get kind of confusing. This is a point. This is a point on the graph. And then these things up here are intervals.